Hello. Wow, you got
Hello.
company over there.
What do you mean? What are you
Yeah,
talking about?
it looks like are those your groupies following you around? Are you trying to teach you? Are you going on tour teaching people different math and stats? Is that
Well,
what's
that would
happening?
be crazy.
Yeah.
Do you
It's
recognize
not,
these people
it's,
behind?
I don't know if it's probable, but it's possible.
There we go.
Jimi Hendrix. It's not the Jimi Hendrix experience, of course.
Not at all.
I'm gonna say I'm not sure I know who these people are.
Oh, no worries. It's One Direction. Do you
What
remember One
One
Direction?
Direction? Okay,
Yeah.
all right. So we're supposed to talk about hypothesis testing,
Yes.
and maybe we need to know what direction the tail is in, right? Or if it's a one or two tail test, right? So the
There
direction
we go.
here. Well done, well done, well done. Well, are they pretty good? I imagine. Do people, a lot of people know about them?
I hope so.
I'm kidding. I'm
People
kidding.
my age certainly
I've
would
heard
know them.
I've heard of them before. I've heard of them before.
Okay.
I'm sad to say I wouldn't be able to pick them out if I heard them, but maybe after this I will probably go play some of their music and see. I mean, if Jimi Hendrix is their is one of their idols, I guess, or one of their you know examples that they may use, it's not bad. All right, okay, cool. So all right, so let's say we're going to conduct a hypothesis test, right? Okay, lots of times depending on what we're trying to prove, to see if we have evidence to prove some kind of a claim that we have, it really depends on if we're talking about, as an example, the mean of a population equaling something or not equaling something, right? Or if we're trying to make the statement that the mean is greater than a certain amount. Okay, so
Yes.
that's, I believe that that's what we need to know to be able to decide if it's a one tail or two tail test, and specifically what direction the tail is going to be in. If it is a two tail, or sorry, if it is a one tail test, is it going to be a left tail test or a right tail test? Okay. So I think probably, let me see if I can pull up the whiteboard here. Here we are. Sorry. This is always a little bit of a uh, ordeal for me. Just bringing up the whiteboard. Sometimes it shows up for you before it shows up for me. I think I've
Okay.
seen that happen.
Is it showing for you?
It's not showing for me right now. It's not
Ah,
showing for me. So
it
it's
is showing
still
for me.
it's
So
showing
while we
for you.
wait, why don't we talk about the difference between one-tailed and two-tailed questions?
While it's coming
Because,
up.
yes.
Oh, okay. All right, here it is.
Oh, fantastic.
I've got it. Sorry. All right. So if we may have, like, we may want to make a claim that the mean of some population is not equal to some value specifically. We'll call it, I don't know, we'll call it, we'll just give it a number. We'll say it's 5 or something like that. Okay.
Okay.
Okay, so we want to make a claim, we want to show that the mean is something different than 5. So that means for us to be able to set up a hypothesis test, we need to write the exact opposite of this statement. Okay? So if it's going to be, if mu is not equal to 5, the exact opposite of that would be that mu would be equal to 5. Correct? Okay. So when we have uh, our distribution kind of laid out for us, and we're talking about our mean, right? Not equaling or not equaling something, um, should mention that any statement of equality is going to involve the null hypothesis. So that's going to be the big portion of our distribution. It's what we're assuming is kind of happening. But are we going to have enough evidence to reject that null hypothesis in favor of the alternative? Because we may want, this may be our claim, okay, that it's not equal to 5. Okay, so we're going to assume that it is equal to 5. And for something not to be equal to 5, it can end up somewhere really, really a lot smaller than 5 or a lot greater than 5. So there's two different ways that we could have our mean, our population mean, not equal 5. So that would involve a two-tail test. Okay? So if we found, as an example, we had it in a sample of, let's say, I don't know, 50, let's say, and we found out our standard deviation, our mean for our sample was equal to 45, with a standard deviation in our sample of, I don't know, let's say about, let's say 10. Is this enough evidence to be able to reject this null hypothesis? Okay? Does that make sense? All right, cool. So in our particular case here, for us to be able to, we would have a test statistic. So it's going to be a Z statistic in this particular case. Just because our sample is above 30, we can use our normal distribution. We don't have to necessarily use the T distribution. Our test statistic to tell us where we're going to end up on this distribution, if we are far enough away to say, well, we assumed it was equal to 5, but we've got evidence. Sorry, I should say 4.5 here. And maybe
I was going to say
call
45
this,
does seem quite different.
Maybe call this, instead of 10, I'll call it 0.1. Yeah, that's probably a little bit better. Sorry about that. Okay.
Okay.
So we haven't yet described one particular value here that's going to let us know where specifically these borderline bits are going to be for this two-tail test.
Mhm.
What is that?
Well, those are going to be our critical values, aren't they?
Well, our critical values are going to come up, but we need to know what before we are able to get those critical values.
Ah. Is this the 1.96 one?
This is 1.96. We're going to end up getting here at 1.96. Sorry, negative 1.96 and 1.96. That's correct. But that comes from our what? Our level of significance.
Oh, right.
Right? How much error are we allowing ourselves? Right? And that 1.96 that you mentioned, that is what we get for our critical values when we have a 5% level of significance. So yeah, those are the values that we see, over and over and over again when we're setting up 95% confidence intervals, or we're setting our level of significance to 5%. Yeah, that's exactly right. That's exactly right. So in this particular case, are we going to find ourselves outside of this null hypothesis part of our distribution? Okay, does that make sense?
Yes.
Right, that would be a two-tail test. So we can finish this, or we can let people that are viewing this finish it a little bit later. Should I finish it?
Oh, go ahead.
Might as well. Okay, all right. So let's try. So that means we're going to take our value that we found in our sample, our mean from our sample. We're going to subtract the hypothesized mean, right, which is mentioned in our null and alternative hypotheses. We're going to divide that by our standard deviation, in turn divided by the square root of however many in our sample, right? Okay, so in our case, we'd see that we would end up with, what is it, 4.5 minus the 5 over 1, right, is our standard deviation. 1.0 is what I listed it as, divided by the square root of, what is that, 50? Okay? Right, so let's see what we get here. We get 0.5 up top, all right, or negative 0.5 up top, and then we're being, and so 0.5, I'm going to do a very rough calculation here, negative 0.5, right? That's going to be multiplied by, right? It's divided by 1, so that doesn't matter. And if we're dividing by 40, if we're dividing by the square root of 50, if we're dividing in the denominator by the square root of 50, it's like multiplying by 50, the square root of 50. So that's about 7, isn't it? All right, a little bit more than 7, right? So that means in this case, I'd end up getting about negative 3.5. And we can see that that is, well, on this side of that distribution. So we can say that it's not equal. We've assumed this, but we were able to reject this null hypothesis in favor of this, proving that it's not equal, right? Two-tail test, right? All right, so if we were dealing with a different claim, right? Let's say I'm gonna put in a new page here. Okay, let's see, page 1 out of 1. Can I put in a new page? I can. Okay. Let's say instead that we wanted to make the claim that the mean, right, was less than 5.0. I think that's what I used before, right? Less than that, as opposed to just not equal to it. We would write down, so let's say that's our claim. That's what we want to prove, right? And if you do want to prove something, if you want to say that you actually proved something, you always want to word it in the in terms of the alternative hypothesis, where we have the strict inequality that represents the alternative, which you can actually prove by rejecting the null hypothesis. If we don't reject the null hypothesis, we really haven't proven anything. We just don't have enough evidence to prove otherwise. Okay, so that we will write down our exact opposite, right? So if it's not less than, it's greater than or equal to 5.0. Okay, and in this case, right, we're assuming, right, the null hypothesis in this case is a statement of equality, right? So there's our null hypothesis. This would be the alternative. So if I'm assuming, right, this is what I'm assuming. This is the big part of that distribution, right? We're assuming that that big part is greater than or equal to something, aren't we? That's what this is showing right here, right? That's what this is showing. We're assuming that it's greater than or equal to something. So that means it's going to tend towards the right end of this graph. So the big portion is going to be somewhere in this direction. Press the button way too soon there. It's somewhere in this direction. So that means the tail, it's going to be a one-tail test, and more specifically a left-tail test. Because this is the part that we're assuming.
So we are looking only in one
Say that again?
direction.
One in that right direction. The right direction, one direction.
I said one direction, but
one going off in this case to the left. And we could use that whole, way of kind of thinking, okay, the big portion has to be greater than or equal to something. Or if it's written in terms of our mean and then some inequality, right? And then some value, so mu less than 5 or mu greater than 10 or whatever it happens to be, we can use this sort of as a mnemonic device to let us know that the tail is on that side. Okay, it's not the most logical way to look at it, but it works nicely. Okay, is that right?
The other way around. So if the inequality was the other side, we'd be looking in the other direction.
That's exactly right. So if I had, instead of, let me see if I can erase this. Instead of this bit right here, if I had greater than, right, that means that the big portion would have to be
the opposite.
Less than or equal to, right? So the smaller portion sorry, the bigger portion, the null hypothesis, this bit right here, would have to be less than or equal to something. So that would give us, forgive me for doing it, trying out here, the big portion would be in this direction. So here's our h sub 0, and there's where the cutoff point is. And again, our tail is going to be the direction that this inequality is showing us. So,
Yes,
yeah, does that make sense?
it does. So
All
it
right.
doesn't matter what direction the question is going in. A one-tailed test will only look in one direction. If we are looking in both directions, we need a two-tailed test.
Yes, that's exactly right. That's exactly right. If we've got as our null hypothesis, sorry, if we've got, I should say, yeah, if we got as our null hypothesis, right, as our null hypothesis mu is equal to something, that's going to be a two-tailed test automatically. Because it could be, because the difference could be either very, very positive or very, very negative. Okay, it could be either on either side to be not equal to something, right? As soon as we see, so that would be our null. So if our null hypothesis was mu was greater than or equal to some value, that means I have to divide it so that the big portion is greater than or equal to something. That would be in this direction, wouldn't it? Oops, God, that I don't know why that does that. Let me try that one more time. That would be in this direction, wouldn't it? Right? That's where our null hypothesis, sorry, that's where our null hypothesis would be in this particular situation. And then again, mu less than or equal to some value, the big portion needs to be less than or equal to something. So that means we stay away from the higher end. Right? That make sense? All right, cool. Great, great. So we have a little bit of time. Shall we discuss p-values or leave that for another video?
We discuss p-values in relation to one and two-tailed tests.
Okay, great. Yeah, so all right, yeah, that's a great idea. So let's say we have, let me add another page here. So the p-value, just to give a little bit of a summary, right? Wherever we get our test statistic, okay? So before we got it at negative 3.5, I think was what we got as our test statistic. That's what our data, that's where our data told us we were on the distribution, right? The p-value that we have in that particular case, because it was a one-tailed test, right? Is that what we said?
The first time was a
Oh,
two-tailed test,
it
but the
was a
second time
two-tailed
was
test. Okay.
one-tailed.
The two-tailed test. Okay. So if it was a one-tailed, so really the only difference is when you look at a p-value, okay, which comes from a test statistic, which there's only one test statistic, right? For a one-tailed test, it's going to be whatever that area is that's more extreme than that test value. So if we said that this was 3.5, negative 3.5, the p-value is the area associated with that test statistic. Okay. If it's a one-tailed test, that would be the only value we'd be concerned with. Okay. Because if we have our distribution, let's say, let me draw another picture here. Okay, so let's say for our two-tailed test, I think this was negative 1.96. We ended up getting a value out here, which was negative 3.5. That's this area, our p-value is this area right here. Okay, so that lets us know what area is more extreme than that test value. And what we're able to do with that is compare it directly to to the level of significance. So our levels of significance would be oops, that's a different, I need a different color here. Come on. Let's use this color. So here, this would represent all the way into that darker, or all the way into that p-value, that would represent our alpha. So our alpha being 0.05, here our p-value, which is just represented by this, is going to be definitely less than 0.05 in this case. So significantly different in this case. If that happened to be a two-tailed test, so we'll use the same value, negative 3.5, but in a two-tailed test, we'd have something that looked like, okay, we would have as our mean, sorry, right, that was a one-tailed test. So for a two-tailed test, which would be where our mean, let's say, is less than 5.0, right? Our negative 3.5, right, would still give us a certain area according to this, right? Wait a minute. I'm sorry. I think I goofed up there, didn't I? Before was a one-tailed test. For a two-tailed, yeah. So I'm sorry. Let me make this adjustment if I can.
Sure.
We're back on the previous one. I think that for a one-tailed test, this wouldn't be negative 1.96. I think this would be negative 1.645, I believe. Because all of this would represent the 0.05, as opposed to 2.5 on one side and 2.5 on the other. Okay? We'd still be well past it with the negative 3.5, but yeah, that would be a mistake. So that's just the p-value just being exactly what this area is that's beyond the test statistic. This bit right here would be our p-value. Alternatively, when we're talking about a two-tailed test, so let me get back to this, our two-tailed test, that may still be our test statistic, but if it's a two-tailed test, meaning that this bit right here would be equal or not equal, right? So mu being equal to 5 or mu not being equal to 5.0, there would be two critical values drawn here and here, right? So that would be the negative 1.96 and the positive 1.96 to capture that middle 95%, as opposed to the first 95 or last 95% in a one-tailed test. So this being a two-tailed test, we basically find out where our test statistic is. Here we found it to be negative 3.5. But since it's a two-tailed test, I've also got to consider exactly the same distance on the other side of 0. So in this particular case, 3.5, positive 3.5. Okay? And what the p-value does is the p-value in this particular case is not only this bit right here that's further away than negative 3.5, but it also tacks on the area that's in front of positive 3.5. So all that would happen, so if when you run a test and you can look at your p-value, and if it considers it a one-tailed test or a two-tailed test, the one-tailed test p-value is going to be half of what a two-tailed test is, because there's an interpretive dance for this if you want to see it. Right? You want to see it?
Sure, go for
Or
it.
should I spare you? All right, I'll show it to you. Here it is. Okay, so here, 0 is right here, right? And here's the distribution going this way, right? So if it's wherever your test statistic comes up, so let's say it comes up on this side, right? You put up your other hand the same distance away from your nose, and then go out. Okay, did you see that? Okay, do it again. So, right, whatever the one tail is, then the next tail, and then this is your p-value, and you move out. Okay? All right. If no other good, if it's not pleasing to watch that particular dance, at least it's got some kind of value beyond just, being a nice dance, I guess. All right. Okay. And I feel it's kind of appropriate to do a dance because we've got our pals back there One Direction. In this case, two directions, if it's a two-tailed test.
Oh, yes. We're moving in both directions with
The two-tailed test,
Oh,
but
boy.
only one direction with a one-tailed test.
Yes, yes,
So
yes. Yeah.
if viewers
Alright.
are able to take away one thing from today, it's just one-tailed test go in one direction, two-tailed test go in two directions.
Two directions. Good, nice. So it's summed up nicely. All right, that's a great point.
There we go.
Wouldn't you say?
Absolutely.
Ah,
Great.
all right.
Good talk.
All right. It was nice. It was nice. It was very nice. All right. I'll talk to you soon. Okay.
All right. See you soon.
Bye bye.